name is Matthias Grote, and I will present the VERMEER Dispersant and Oil tool, which was developed during the project, together with Artur Radomyski, who was here as a postdoc, and he was not here today in the meeting, but he will be there tomorrow to show you the tools when you take hand on the tools. So I will present the general introduction, and the technical details will be then there tomorrow. So we will talk about chemical fate in a simple aquatic ecosystem. And just for giving you a little bit of the idea why we did this, the VFR, or a small part of the VFR, is involved in advising the Central Command for Maritime Emergencies in Germany, and their spill managers have to consider what they do in case of a marine oil spill. So they have to find solutions to choose which response would be effective to minimize the damage to the environment and to human health. And so there are a lot of technical choices to be made, but one important choice is whether to use dispersants or to rely on other response measures. And so what are dispersants and how do they act? Actually, it's like if you imagine an oil slick on the surface of the water and you add a dispersant. This is like a surfactant with some kind of solvent inside, and which will act on the surface of the oil slick and will promote the dissolution of this oil slick into small droplets. You can imagine it's something like you do your dishes. You add something to get the oily part dissolved in the water phase, and you break up larger oil volumes into little droplets. And this has several advantages. You reduce the surface slick of the oil, and you also reduce the wind drift, because the oil slick on the surface will be pushed by the wind to wherever the wind goes. And also you reduce the oil reaching the shoreline if the wind coming ashore. It's also considered as a protection of seabirds, and in the end also because you increase the surface area of the oil droplets, you can enhance biodegradation. On the other hand, you have higher bioavailability of the oil components to pelagic and benthic organisms. And also the oil can be incorporated in the sediment where it would not normally reach. So what we did in another project here, just to show you the idea, this was with some colleagues from another institute who simulated two oil accidents, one where the blue ship is sinking and the other where the red ship is sinking, and simulated what would happen given the meteorological conditions. Let's say the wind, the waves, and the currents. Where would the oil end up within 5 days? And so we have two scenarios, the blue and the red, and the little dots is where the oil would end in case of dispersion, and the big dots is where it would end if it stays on the surface. And what we can see here is that in case of non-dispersion, the oil slick will end up on the coast or in the green area. It's a Wadden Sea. It's a sensitive ecological area. And so in this case, because we have often northwestern winds in the German coast, the dispersion could reduce the amount of spilled oil reaching these sensitive areas of the coast. Typically, what is done is that you do a net environmental benefit analysis to look what are the pros and cons for each option. And in this case, it is a benefit if we keep the oil outside of these sensitive areas. But what actually is not really regarded in this kind of analysis is what happens actually with the oil which is shifted inside a specific zone. So how does the oil use influence the environmental fate of the oil components? How does the exposure of different organism groups is altered? And in the end, also, how is the human exposure modified? So the question which we wanted to tackle is how can dispersant use also be an option inside of the sensitive zone? So when we don't replace the oil, but just to put it to some other compartments. So in the environment, we typically have very complex ecosystems and food webs. This is just to illustrate. I won't go into detail of this. It's just to show that there's a lot of interdependence of organisms with feeding nets. And so it's a complex thing. So we have also multiple exposure pathways in such a situation via the water phase, via food, via dermal contact, via inhalation, and then could target different environmental species. But also for humans, like this is a very touristy area where people go barefoot on the mud flats, and so also a human exposure could be inferred. So what happens if we have an oil spill? So there's a very simplified representation. We have a water surface in the ship, and if there's an oil accident, so oil coming to the water surface, we will have a oil slick forming in this water surface. And there's always also some natural dispersions. That means that via the wave action, the surface slick will to some extent break up and little droplets are formed, which are then entrained into the water phase. And these little oil droplets are then somehow floating in the water phase. Another phenomenon which is observed is the dissolution. So you have some parts, and this of course depends also on the compounds, on the solubility of the compound. They will resolve in the water phase. And so you have some part of the oil that will be a dissolved fraction. And of course, you also have the solution from the oil droplets. So this is more or less what happens in the water. But then you have the exposure of organisms. And so you have some kind of contact of organisms with the oil droplets and with the dissolved oil components. And an oil accumulation which takes place in the food web, so in the different organisms. And this happens anyway, but by adding a chemical dispersant on the oil fleck, we can shift oil towards more oil droplets. So we have less surface slick, but we have more oil droplets, and this will also induce more dissolution because we have a higher surface area, and very likely also a higher bioaccumulation in the food web. So in the oil dispersant case study in this project, we relied on tools which have already been developed, like Philippe presented earlier, the models in the Merlin Expo, which were developed to simulate uptake of compounds in organisms via ingestion or via respiration. And for the project, we used these elements of the model, but we had to develop new ones because oil and oil dispersion was not yet included in the model. So we had to include in the model new modules which allowed for simulation of the oil droplet formation and for the oil resolution from droplets or from the surface area. And this multimedia model modules were developed during this project to put forward this dispersant case study. And in the end, the idea is to have some time-dependent concentration of the different petroleum hydrocarbons in the water and the different compartments. So this you have already seen in a similar way by Philippe. And in the top left, you have the new module, which is the oil module, which was developed to include the different processes we have just talked about. And in the end, there are all these little boxes where you see the flash shows some transfer process. So the uptake of oil components via the water phase, or in the higher trophic levels, also via ingestion via the food. So the fish that might eat some kind of crab would also incorporate the oil which has been uptaken by the invertebrate earlier. So there's a lot of processes involved, and it is not possible, and I think you would not like to go into detail in this presentation. There's a very good documentation of all this available, but just to give you the idea, we have a lot of processes which have been included in the model, and state variables and forcing variables. For example, the solution is one parameter which went a little bit bigger. The SE is the solubility of the compound, and the state variable in the end is the concentration of this compound in the water. And if in another case, for example, if we look at the adsorption, this is how the compounds binds to sediment, organic matter, and there the parameter which is most important is the KOC, so the distribution coefficient between the organic carbon and the water phase. And so the binding or the state variable is the concentration of the compound in sediment. And in this matrix here, which is now more complex because we open one of the box, you can see that inside of each of the boxes there's a lot of processes involved, just to show you how this looks like, but we will have a closer look to that tomorrow when you take hands on the tool. But you can see already that there's a lot of state variables and processes that were parameterized in this model. So for the case study, we have not only the processes, but we also have the system we are looking at. And this is something which is always some kind of individual scenario we are looking at. So just to show you, for example, in this case, we looked what actually how does a herring, which is a very important fish species in the North Sea area, how does it feed? So it eats a lot of different crabs and smaller fishes, and so we tried to simulate the food preference of this species via a relative distribution of food items which might compose the diet of this species. So this is a kind of aspect from the food web. And then, of course, we have to look at the target compounds we are actually looking at. So there are different petroleum products. And in this case, it is, of course, possible to give different inputs of these compounds. And oil is a very complex mixture of a large number of hydrocarbons. So what we did here is some kind of simplified list of hydrocarbons, which are typically components in oil. And so we have some kind of pseudo compounds, which were then used for the modeling. And then in the end, you can simulate all the compounds, or just look at one specific, maybe especially toxic compound for certain species groups. And yeah, so and then what can be done with this model? So what we want to know is which compartment will be the most affected by the oil, how the concentrations in the compartment will evolve over time, and how does the increased dispersion modify the exposure of different organism groups. And this is all with the intention to provide advice to the spill response people who have to decide on the best spill response option. And this is just one example to show you what can come out. Of course, it depends on the specific scenario you're looking at. So which amount of oil is regarded, how large is the area which you regard where the oil distributes. And here we have, well, the axes are not visible. On the y-axis you have the concentration, and on the x-axis you have the time. So, and the red one is and the blue one are different oil types, and here we have just represented the aromatic fraction of C16 to C21 compounds. And on the left-hand side, you see what concentration would be expected in the water column below the surface slick in case of no dispersion. And on the right-hand side, you have the case of a dispersion where the dispersion to oil ratio is 1 to 20. So you add a lot of dispersion to the oil slick. And what you can see is that you enhance the concentration of the oil in the water about a factor of 2 to 3, maybe in this case. So this is the concentration in the oil, in the water phase. And then if you look at the exposure inside the organism, in this case it's a herring, you also see that the exposure of the fish will be higher in the dispersant case, but it's only a period of time, and then it will go more or less into similar concentrations as if you had no dispersant. Of course, this is the result of a very special case, which was just simulated here, but you can, of course, adapt all the parameters for your special case if you are interested in this. And as Philippe said, in the Merlin or in the VERMEER model now we have some kind of predefined scenarios which can be then just adapted to the special questions you might have. So this is already the overview on this part of the project, and I thank you very much for your attention, and I think we have still some time for questions.